Okay, and then in this video we shall discuss about the linear motion variable capacitor and a linear variable differential transformer in sensors of motion. The sensors of linear motion. So here variable capacitor LVDT. So linear motion variable capacitor, you can see the diagram here. So here you have a two capacitor, the plates which is connected here. These plate, in these two plates, one is movable plate and one more is a fixed plate. Here you have an arm which is connected to a movable plate, and the difference between these two is a connection to the measurement or a control unit. So the circuit is very simple here. So the thing you need to remember here is how it is being connected actually. So here the function is a linear motion into the changes in the capacitance. It converts a linear motion into the changes in the capacitance. You can see an arm here in this plate. This is movable. Okay, when you move an arm, this plate will move towards the fixed plate as well as back to the fixed plate. So here it consists of two plates, and one is a fixed plate and one more is a movable plate. It is separated via air or a dielectric. Air, it is nothing but a dielectric. The movable plate is linked to a moving component via an arm. Movement to the right, the movable plate moves closer to the fixed plate in order to increase the capacitance. So understand it, by using an arm we will move the movable plate towards the fixed plate. When it is moved towards the fixed plate, the capacitance will increase. So if it is moved away from the fixed plate, capacitance will decrease. So this is how it actually works. So changes in the capacitance is mainly dependent upon the movable plate. So it is all about the diagram, what you write, how you explain it. Diagram should be very perfect when you are writing, when you are explaining. Okay, this is about a linear motion variable capacitor. The next is a linear variable differential transformer. You can see the diagram here. So this is a arm, housing and a AC source. So it is connection of a differential winding for an AC input. You have a two winding here. So there is a housing again, there is a AC source, SW1, SW2 and PW. There is a arm. Let us look into the working of this. So here again you have a arm and a core which is connected. So here this is connected into an housing. This core arm is where it is movable, where the core has been moved. So let us look into the formal working of this. Coming into the function of this, it converts a linear motion into the voltage signal. So the components which are used here is a primary winding, two identical secondary winding SW1 and SW2, soft iron core connected to a moving component, and you have an operation. Normally the core is in a central position where the voltage SW1 and SW2 are equal, and rightward movement, it increases the voltage in SW1 and decreases the voltage in SW2. In the leftward movement, it increases the voltage in SW2 and decreases the voltage in SW1. The amount of voltage changes in each secondary is proportional to the core movement. As I had said you that this core is a movable. This core movement, when you move it, uh, when it is moved towards the rightward, S1 will increase, SW1, SW2 will decrease. When it is moved leftward, it will increase in SW2 and decrease the voltage in SW1. So this is actual working of it. Let us look into the output signal and DC output. So we have an output signal here again. The secondary winding can be connected to produce a net output signal. At null position, the net output is 0. So any movement from null position results in one secondary voltage increasing and other decreasing, effectively doubling the net output. So DC output, the AC output from the LVDT can be rectified to produce a DC signal. So what do you mean by DC? It is nothing but a direct current. So AC output from the LVDT can be rectified to produce a DC signal. The rectifier and a resistor are used to convert AC to DC. RC filler smooths the DC signal for an accurate position measurement. These sensors are essential in industrial application where the precise measurement and control of linear movement are critical. They provide a reliable electrical signal that correspond directly to the mechanical motion, ensuring the accurate monitoring and automation process. Next topic we discuss here is, we have the last three topics of the module 5. Those are about the strain gauges. You have the question will be asked in this way: define strain gauge and explain the mechanical strain gauge. Define strain gauge and explain electrical strain gauge, and define strain gauge and explain optical strain gauge. So here strain gauge is a device used to measure the amount of strain or a deformation in an object. When the object deforms, the strain gauge deforms as well, causing its property to change. This change can be measured to determine how much the object has deformed. So coming into this is a definition that will be common to all the strain gauges. So you need to understand the strain gauge is a device used to measure the amount of strain in an object. Okay, here the strain means deformation. So in overall everywhere we have used the deformation, it means a strain, you need to understand. So coming into a mechanical strain gauge. Mechanical strain gauge use mechanical method to amplify the deformation, making it easier to measure. These gauges have built-in system for magnification and do not require any additional equipment. The types of mechanical strain gauges are Berry type, Hagenberg type. So in the Berry type, it uses a basic mechanical principles for magnification. In the Hagenberg type, it is very more complex and precise, often used in advanced application. Coming into a magnification mechanism, early design used a single mechanical lever with a magnification of 10:1, the meaning the gauge showed 10 times the actual deformation. So early designs, they are saying that there was a 10:1 magnification. These worked well with a long gauge length. In the modern design uses a compound level with a magnification up to 2000:1, making them suitable for smaller gauge length and providing much higher precision. Coming into an advantages, the self-contained. The mechanical strain gauges do not need any external equipment for magnification. Ideal for static test. They are best suited for static measurement due to their self-contained nature. Coming into a limitation, high inertia and manual reading. So coming into high inertia, these gauges are not suitable for dynamic measurement because their high inertia makes their response slow. In the manual reading, there is no automatic reading of recording of reading, which can be a limitation for continuous or precise measurement. So when they ask you about the gauges, you need to explain what do you mean by gauges, and then these are the few things like types of mechanical strain gauge, magnification mechanism, advantages and limitation, or the few examples of the mechanical strain gauge.